Something happened near the Sun that no one can explain. An interstellar object, known as 3I Atlas, entered the inner system on what should have been a predictable terminal path. It was supposed to burn, to fracture, to fade. Instead, it did the opposite. In the span of minutes, its entire chemistry changed. The surface brightened, its coma collapsed, and then the glow turned blue. Deep, electric, unnatural blue. Instruments froze. Satellites went offline. Even the solar wind seemed to bend around it. When the data finally returned, 3I Atlas was no longer behaving like a comet. It was colder where it should have been hot, heavier where it should have evaporated. Its orbit remained stable, but its reflection doubled, as though the sun had tempered it instead of destroying it. No known model accounts for what came next. The electric field pulse, the synchronized magnetic rhythm, and the faint resonance that echoed through the solar plasma. It was as if the interstellar object had not only survived the fire, but adapted to it. Now the question haunting every observatory isn't what 3I Atlas is, it's what it has become. This is the 3I Atlas channel, calm, focused, and based on real-time solar system data. If you want to be part of this mission, hit subscribe right now. Comment Atlas below to enter the giveaway for our exclusive 3I Atlas hoodie. Tell me where you're watching from and the exact time it is. You're now part of a global community tracking something the textbooks never prepared us for. At 0419 UTC on October 30th, 2025, the Solar and Heliospheric Observatory recorded a comet behaving exactly as predicted. 3I Atlas, an interstellar wanderer already known for its carbon dioxide-rich composition, was nearing the end of its perihelion arc. It was surrounded by radiation and plasma winds strong enough to vaporize almost anything known to science. Its coma glowed in the familiar emerald green hue, a color produced by diatomic carbon fragments reacting under ultraviolet light. Then, just 4 minutes later, everything changed. At a 4:23 UTC, the emission line that defined its optical fingerprint suddenly disappeared. In its place appeared a sharper wavelength at 465 nanometers, a deep electric blue that no one expected. The shift was instant, not gradual. There was no fading from green into turquoise, no soft blending as the comet warmed. It was a clean switch, a full transformation. The brightness doubled, the temperature curve spiked, and then every instrument turned away as automated protection systems activated to prevent damage. Those missing 8 minutes of raw data have already become legendary among astronomers. For the public, they are a mystery. For scientists, they are a threshold between predictability and the unknown. When the feed returned, 3I Atlas was still intact, trailing a long, faint blue wake that stretched hundreds of thousands of kilometers behind it. Its size remained constant, its orbit unchanged. Yet the object no longer looked the same. Its color, its light, its very presence seemed rewritten. How could something change so completely in so little time? The first explanation points to thermal phase transitions inside the nucleus. Atlas carries carbon-based compounds that react violently to ultraviolet radiation. As it skimmed just over 1 astronomical unit from the Sun, the outer layers may have reached the critical point where carbon monoxide ice does not simply vaporize but breaks apart into atoms that glow blue under extreme energy. For that glow to spread evenly across the whole coma, the process must have been synchronized throughout the surface, not limited to random vents. That synchronization is what alarms researchers most. Cometary activity is usually chaotic. Jets flare up and fade as the body rotates. Here, the change occurred everywhere at once. One possible explanation involves magnetism. The solar wind could have induced electrical currents through the comet's outer shell, aligning charged particles and forcing a global chemical reaction. In that instant, 3I Atlas may have become a conductor, feeding on the very plasma that threatened to destroy it. Another possibility is photochemical reflection. As the intense radiation stripped lighter gases away, heavier molecules might have condensed into microscopic crystals. Those crystals would scatter blue light more effectively than green, turning the whole coma into a temporary mirror. If that happened, the color shift was not emitted but reflected, a new skin forged by heat. Both ideas lead to the same conclusion. The comet did not collapse under solar stress. It adapted. Later analysis revealed another clue. Polarization data showed the light had become unusually organized. Dust within the coma was not scattering light randomly but in a coherent pattern. That can only happen if external forces align the particles with precision. It reorganized itself, one mission scientist noted in a private report that soon leaked online. The phrase caught on. The moment of transition. The instant when a body from another star behaved as if it possessed intent. The timing remains the most puzzling detail. The shift happened exactly when a solar flare erupted, the two events linked by seconds. Coincidence is possible, but resonance feels closer to the truth. For 4 minutes, the laws of comet behavior bent towards something new. 3I Atlas crossed an invisible boundary between chemistry and response, between reaction and adaptation. It did not just survive the sun, it changed because of it. And that single transformation, preserved in a few frames of data, may be the first evidence that even a frozen fragment of another world can learn to evolve when faced with fire. Colour is not a decoration. It is information carried by light. Every wavelength tells a story about energy, chemistry, and transformation. In the emptiness of space, where there is no air to scatter light, colour becomes pure signal. It reveals what matter is doing at that exact moment, how atoms move, and how they break. For 3I Atlas, that signal changed in a way that shocked every observer on Earth. Before its closest pass to the sun, the comet glowed in the soft green shade familiar to astronomers. That tone comes from carbon molecules that release a faint emerald light when sunlight breaks them apart. It is the same chemical fingerprint seen in many comets that pass through the inner solar system, but as Atlas moved deeper into the field of solar radiation, that familiar green faded and an entirely new colour took its place. The comet turned deep blue. Blue in space is rare. It means the energy inside a material has risen far beyond normal. The electrons that orbit its atoms are not only excited but pushed so far that they leap away entirely. When they recombine, they release light with higher energy and shorter wavelength. In laboratory experiments, this happens when carbon monoxide gas is ionized by extreme ultraviolet light. But the sun's energy near perihelion was not intense enough to explain the sudden change. Something else must have happened within the comet itself. To understand the puzzle, scientists looked at what a comet really is. It is not a solid stone, but a fragile mixture of frozen gas and dust, held together by gravity and time. Deep inside are pockets of trapped material that react the instant they meet sunlight. When one of those pockets ruptures, gas rushes out violently, forming a luminous halo. In the case of Atlas, that outburst might have been so strong that it charged the surrounding cloud of dust and gas, turning it into a temporary plasma field. Such a field would naturally emit a blue glow, not from reflection, but from energy released by ionized molecules. There is another layer to the mystery. The blue colour appeared evenly across the entire coma, not in scattered patches. That means the process was not local, but global. The whole surface must have reacted together. One possible cause is an electromagnetic pulse triggered when the solar wind swept past the comet's ionized tail. The moving plasma could have induced electric currents through the comet's shell, setting off a synchronized chemical response that changed its light in one instant. In a perfect vacuum, color behaves differently. Without air to scatter and absorb, even a small change in particle size can shift the visible tone completely. If the dust around Atlas reorganized into finer grains or metallic crystals, it would reflect shorter wavelengths and absorb longer ones. The result would be a blue hue, even without any change in chemical makeup. Under intense sunlight, those grains could form within seconds, covering the nucleus with a thin reflective layer that amplified the color we saw. The most puzzling part is how long the blue lasted. Normally, such ionized gas fades within minutes, yet Atlas remained bright and blue for almost half an hour. That persistence suggests a stabilizing field surrounding it. Instruments later showed faint magnetic oscillations near the time of the event. Some scientists believe the comet briefly generated its own magnetic cocoon, trapping charged particles and feeding the glow until the field collapsed. Color in vacuum is not just a visual effect. It is the story of energy moving through matter without resistance. When 3I Atlas changed from green to blue, it showed that color can act as a record of transformation, a living measurement of survival in sunlight. In that deep electric blue, Space revealed that even frozen fragments from another star can speak through light if we know how to listen. When scientists talk about a spectral break, they mean a place in light where the pattern of colour and energy no longer follows the rules. Every object that shines has a spectrum, a fingerprint of wavelengths that tells what elements it contains and how they behave. For comets, that spectrum is a map of chemistry in motion. Each spike and dip marks a molecule being broken apart or a gas being excited by sunlight. The pattern is usually stable. But when researchers examined the readings from 3I Atlas after its sudden blue transformation, the map was torn in half. The usual green signature of carbon compounds vanished completely. The oxygen lines that should have appeared just beside them were missing as well. Instead, strange new peaks rose in the blue and violet regions, stronger than anything ever recorded from a natural comet. At first, technicians thought the instrument had failed. The data looked like interference, a corrupted feed, maybe static from the sun's radiation storm, but the same pattern appeared on every telescope that captured it. The break was real. To grasp how strange this is, imagine listening to an orchestra where all the violins and flutes stop playing mid-note, replaced by instruments no one has ever heard before. That is what the spectrum of 3I Atlas looked like. The familiar harmony of elements disappeared, and a new composition took its place. For a few minutes, the comet stopped behaving like frozen rock and began to act like a plasma body, radiating pure emission light instead of reflected sunlight. The missing oxygen puzzled researchers most. Comets release oxygen when water or carbon dioxide breaks apart under heat. Even a dying comet should glow with faint red and green oxygen lines. The absence of that light suggested either the gases had been stripped away or something was absorbing their photons before they reached us. One explanation is that a dense layer of charged dust formed around the nucleus, a shell that filtered the outgoing light. Another is that the oxygen was trapped in complex molecules that prevented it from glowing freely. Both ideas hint at chemistry we have never seen in natural space ice. Then came the nitrogen. Its spectral lines grew stronger by the minute. Nitrogen is a shy element, difficult to excite, but it dominated the readings after the break. In ordinary comets, nitrogen compounds make up a small fraction of the total gas. In Atlas, they briefly became the main component. That inversion defies every model of comet composition. The change suggested a rearrangement deep inside the core, as if heating had forced gases to migrate through layers of different materials, bringing the rarest compounds to the surface. Some scientists described it as phase separation on a planetary scale. Others suggested photolysis, a rapid breakdown of complex organics into simpler fragments that glow blue. Either way, the numbers did not add up. The intensity of the lines was too high for passive chemistry. It was as if the comet had amplified its own light. The term spectral break quickly moved from datasheets to headlines. It became the symbol of something that could not be explained by heat or distance alone. Within hours, simulation teams began running plasma models to see whether electromagnetic resonance between the comet and the solar wind could cause such a shift. The results were inconclusive, but the idea gained traction. If charged particles spiraling through the coma reached the right frequency, they could boost certain wavelengths and erase others. The comet would literally edit its own spectrum. When the recordings were later compared from observatories in Chile, Hawaii and India, the same break appeared across all datasets, timed within seconds. No equipment error, no local interference. The universe itself had drawn a line in the light, separating what we understand from what we do not. That sharp divide became known as the spectral break. For the scientific community, it marked the moment 3I Atlas stopped being just another interstellar visitor and became an active participant in the solar system's energy exchange. For a brief time, it did not simply reflect sunlight, it wrote new light of its own. Heat is supposed to destroy comets. That is one of the oldest certainties in astronomy. As they fall toward the sun, the ice that binds them begins to sublimate, releasing gas and dust in bright jets that tear their surfaces apart. When the heat becomes too intense, the nucleus fractures, and what remains drifts away as a fading trail of debris. It is the same story every time, but 3I Atlas did not follow that story. Instead of breaking apart, it brightened. Instead of cooling after perihelion, it stabilized. The closer it came to the sun, the stronger its structure appeared to become. Thermal models predicted the opposite. Based on its trajectory and estimated composition, The surface of 3I Atlas should have reached 700 degrees Celsius at closest approach. That temperature is enough to vaporize most known ices and even melt some silicates. Yet brightness data from solar probes showed the comet reflecting more light than before, nearly doubling its albedo. The surface, which should have been covered in dark carbon soot, turned highly reflective. The heat seemed to polish it rather than burn it. Scientists began referring to this contradiction as the thermal puzzle. Every instrument pointed toward the same impossible conclusion. 3I Atlas was becoming more ordered, not less, as it faced the sun. Normally, when ice sublimates, the escaping gas creates pressure pockets that cause explosions and fractures. Instead, the comet's surface emissions became uniform and steady. The temperature gradient between its sunlit and dark sides flattened instead of widening. It was as if the object had found a way to manage heat, redistributing energy evenly across its body. One theory proposed that the comet's carbon dioxide composition acted as a natural coolant. Carbon dioxide sublimates at lower temperatures than water, carrying away heat more efficiently as it escapes. In that sense, 3I Atlas could have created its own thermal regulation system, a kind of passive refrigeration that balanced its temperature by venting gas continuously. But even that process should have eroded the nucleus. Radar reflections later showed that its shape remained nearly identical. The loss of material was minimal. Another hypothesis focused on phase change rather than venting. Perhaps under extreme pressure inside the nucleus, carbon dioxide ice transformed into a denser crystalline form capable of withstanding greater heat. Laboratory work on similar compounds shows that such transitions can occur under sudden temperature spikes, temporarily absorbing large amounts of energy. If this happened within 3I Atlas, the heating could have triggered a structural rearrangement instead of destruction. The comet would have used energy to reorganize itself. Spectral readings supported this possibility. After perihelion, infrared data revealed a narrow emission band associated with solid carbon monoxide mixed with silica dust. This combination can form a glass-like coating that reflects visible light with high efficiency. The more it was heated, the smoother and shinier it became. In essence, the sun may have sealed the comet inside a reflective shell. That shell would reduce further sublimation, allowing it to survive longer than expected. Yet even with those explanations, the timeline remains wrong. The brightening occurred too fast. The transformation from dark green to pale blue-white took less than half an hour, faster than any known thermal process in a vacuum. Some researchers believe the comet's rotation slowed precisely at that moment, spreading solar heat across a wider area and preventing localized melting. Others suspect electrical forces again played a role. When charged plasma from the sun interacts with a conductive surface, it can deposit energy unevenly, forming electric currents that rearrange surface material. In that scenario, the heat did not simply cook the comet, it restructured it from within. When the comet finally moved beyond the sun's glare, its brightness curve remained almost constant. For 3 full days, no collapse, no fragmentation, only a slow, graceful dimming as it cooled. The event forced scientists to rethink how fragile interstellar bodies behave in extreme conditions. Heat, once considered a destroyer, might also be a sculptor. In the case of 3I Atlas, it may have served as the architect of a surface that learned how to endure the furnace of a star. That is the heart of the thermal puzzle, how something frozen for millions of years could meet the sun and emerge stronger. The question is no longer why it survived, but how it learned to use the fire to hold itself together. The phrase sounds impossible. Solid plasma. 2 words that should cancel each other out. One means rigid, the other means chaos. Yet when researchers studied the data from 3I Atlas during its colour shift near the sun, that contradiction became the only description that fit. For a few brief minutes, the comet behaved as if it were both matter and energy at once, holding a structure made from motion itself. Plasma is the 4th state of matter, a form in which atoms are stripped of their electrons and move freely as charged particles. It is what stars are made of, what fills solar flares and lightning bolts. Normally, plasma cannot hold shape. It is fluid and unstable, spreading and fading as soon as the energy source changes. Solid matter, by contrast, relies on fixed atomic bonds. The 2 states sit at opposite ends of physics. But there is a narrow and little understood region between them, where electromagnetic forces can organize charged particles into ordered patterns, almost like a crystal. In this region, plasma begins to imitate solidity. That is what some scientists now believe happened inside the coma of 3I Atlas. As the comet skimmed close to the Sun, solar wind slammed into its atmosphere of ionized gas. The interaction created a sheath of magnetic fields wrapping around the nucleus like an invisible cocoon. Instruments detected a spike in polarization, meaning that particles in the cloud were aligning in the same direction rather than spinning randomly. Alignment on that scale requires coherent electromagnetic control. In other words, the cloud was behaving as a single system, not a collection of separate atoms. When sunlight struck this organized plasma, it scattered in a very specific way. Instead of the wide green glow typical of cometary gases, the light concentrated into narrow bands of blue. That kind of selective emission is a hallmark of ordered structure, similar to what happens in lasers or crystalline minerals. For a moment, 3I Atlas seemed to transform its own plasma into a lattice, a semi-solid layer of charged matter that trapped light instead of releasing it freely. The energy required for such a transformation is immense, but the timing fits the data. Solar radiation was peaking during a minor flare that sent waves of charged particles racing through space. The comet was directly in their path. When those particles hit its magnetic envelope, they could have synchronized the motion of ions within the coma, freezing them into position through magnetic tension. It would not be solid in the human sense, but more like a standing wave, energy holding shape. Once that structure formed, it would have acted as armor. The ordered plasma could reflect much of the incoming solar radiation, preventing further heating of the surface. That would explain why the comet brightened without fragmenting. It may have created a temporary shell made purely from electromagnetic balance, a self-generated shield that allowed it to survive conditions that should have vaporized it. A few seconds after the color change, sensors recorded oscillations in radio frequency bands. They resembled the low hum produced by plasma instabilities in laboratory experiments. That sound, translated into data, showed a rhythm rather than noise. The pattern was stable, suggesting resonance. Something within the comet was maintaining the field instead of letting it collapse immediately. When the solar wind weakened, the structure decayed. The blue hue faded and the alignment readings dropped. The solid plasma phase was over. But the brief existence of that state forced scientists to reconsider what a comet can become under stress. If electromagnetic forces can organize ionized gas into stability, then even a fragile object from another star can momentarily cross the line between material and energetic, between object and field. The idea of solid plasma once belonged only to theory. Now it may have been seen in the wild. A comet turned its own destruction into protection, using light and magnetism to hold itself together. In the silence near the Sun, 3I Atlas showed that matter and energy are not enemies. Under the right pressure they can cooperate, forming a structure that is neither fully alive nor dead, but something in between, an island of order sustained by fire. The strangest part of the 3I Atlas event is not what we saw, but what we did not. Between 0423 and 0431, universal time, the stream of data from multiple solar observatories simply stopped. 8 minutes of missing telemetry in the middle of the most significant colour and brightness change ever recorded in a comet's history. Every agency had the same explanation: automatic sensor protection, glare saturation, temporary signal loss. Each reason made sense on paper, but taken together, they left a hole in the story so wide that speculation poured straight through. Solar observatories are designed to operate near the edge of danger. Instruments like those on SOHO and Solar Orbiter constantly watch the Sun's violent surface, using filters to block its blinding light while recording coronal activity in different wavelengths. Their software can detect sudden intensity spikes and shut down to prevent damage. Such shutdowns happen often. But what makes the Atlas case unusual is timing. The blackout began exactly as the comet's spectrum shifted from green to deep blue, and ended just as the signal stabilized again. No overlapping observation caught the missing moment. It was as if the universe paused the cameras. When engineers reviewed the raw logs, they found nothing clearly abnormal. Voltage levels rose slightly in several sensors, enough to trigger automated safety mode but not enough to suggest a system fault. The logs did not mention radiation storms or cosmic ray spikes. For most analysts, that was the end of the discussion. The machines did what they were supposed to do. Yet for those studying the comet's physics, the silence was almost unbearable. Because in that gap may have been the answer to everything that followed. Data is the language of astronomy. Without it, the universe becomes guesswork. The problem is that absence also speaks. A missing signal can mean damage, but it can also mean interference, an overload so intense that instruments could not interpret what they were seeing. If 3i Atlas emitted or reflected energy outside expected ranges, it could have saturated detectors across multiple channels simultaneously. Such saturation would look exactly like failure. The devices would switch off to protect themselves, leaving a blank window in the record. Some scientists think that is precisely what happened. The sudden shift to blue may have been accompanied by a burst of ultraviolet or soft X-ray radiation strong enough to blind optical sensors. If that pulse was brief, lasting seconds rather than minutes, the automatic resets would hide it completely. The evidence would exist only in the shadows of the logs, slight fluctuations in electrical current or signal noise before shutdown. Researchers have found traces of both. Others take a simpler view. They argue that multiple instruments entered maintenance cycles at overlapping times, and the apparent synchronization is coincidence. The comet's position behind the Sun made observation difficult anyway, and the lack of data is just the natural limit of geometry. Both explanations can coexist, but neither satisfies everyone. Silence rarely does. In the days following the event, amateur astronomers combed public archives for any hidden frames that might fill the gap. None appeared. Even spacecraft that were not aimed directly at the Sun recorded brief telemetry interruptions. A few independent satellites captured weak readings in radio bands during the blackout, showing faint oscillations near half a hertz, the same frequency detected minutes later by the Parker Solar Probe. If those signals are connected, they suggest that something powerful enough to disturb sensors across millions of kilometers passed through that region of space. The phrase, data gaps and silence, has since become shorthand among researchers for the moments when nature refuses to be observed. In those empty records lies the boundary between knowledge and mystery. The universe does not owe us clarity. Sometimes it hides its most important, transitions in the glare of its own light. For 3i Atlas, those 8 missing minutes may never be recovered, yet their absence gives the event its shape. The silence between signals defines the sound, just as the blank in the data defines the discovery. What happened in that gap, whether an overload, a pulse, or a natural pause, remains unknown. But the mystery continues to remind us that even in an age of endless observation, the cosmos still decides when to let us see and when to turn the lights off. When the data stream resumed after the mysterious blackout, 3i Atlas was no longer a single glowing point. It carried behind it a luminous thread that stretched across hundreds of thousands of kilometers, a soft curved band of turquoise light winding through the black. It looked alive, like smoke rising underwater. The color was unmistakable. The green coma had vanished, replaced by a cool blue tail that shimmered in waves. For hours, that strange ribbon followed the comet across the solar field, glowing long after most comas fade. Scientists began calling it the blue wake. Comet tails are normally predictable. They consist of 2 parts, a dust tail that reflects sunlight and an ion tail made of charged gas pushed away by the solar wind. Dust tails are yellow-white. Ion tails are blue but faint, often lost in glare. What 3i Atlas produced defied both categories. It was too bright for ions alone, too structured for dust, and its light pulsed in intervals. The wake seemed to breathe. When spectrographs analysed the colour, they found that it peaked near 465 nanometers, matching the wavelength of ionized carbon monoxide, the same signature that had defined the comet's brief blue transformation at perihelion. That connection changed everything. It meant the colour was not a reflection, but an emission. The tail was generating its own light. As the comet moved outward from the Sun, the wake persisted instead of fading, suggesting an internal energy source was feeding it. Normally, the pressure of sunlight and the solar wind would strip ionized gases away rapidly, dispersing them into space. But the blue wake held its shape, curving in elegant arcs as if bound by invisible threads. Magnetometer readings from the solar orbiter recorded weak oscillations aligned with the wake's direction. This hinted at a magnetic structure, a channel of plasma frozen in motion. If true, The comet had carried with it a piece of the sun's magnetic field, trapping it inside its ion stream like a captured current. The field could have stabilized the flow, allowing the gas to remain coherent for far longer than usual. Essentially, 3i Atlas was towing a magnetic rope through space, glowing blue where the trapped ions interacted with sunlight. Images taken 6 hours later showed something even stranger. The wake began to twist. Its shape rotated counter to the comet's motion, forming a spiral that expanded slowly outward. Modelling suggests this may have been the result of differential flow between the dust tail and the magnetic plasma stream. The sun's wind was pulling one side harder than the other, winding the tail like a coiled ribbon. The symmetry of the spiral was perfect enough to suggest resonance. Perhaps the magnetic field and the comet's rotation were locked together, creating a repeating pattern of energy release. Some researchers think the blue wake marked the slow relaxation of the solid plasma state. During its near-solar encounter, 3i Atlas may have formed a shell of magnetized ions. As it moved away and the solar pressure decreased, that shell unraveled, releasing stored energy along magnetic lines. The wake would then be the comet's exhale, the visual trace of a system returning to equilibrium. Amateur astronomers who observed it described the sight as eerie. Even through modest telescopes, the blue glow seemed unnaturally pure, without the grainy texture of dust. It looked almost metallic, like a trail of liquid light. The wake's persistence, more than 20 hours before fading, made it one of the longest-lasting ion emissions ever recorded. For scientists, the blue wake became the key to decoding the entire event. Its composition linked the comet's interior chemistry to the solar wind, its behavior revealed the presence of electromagnetic structure, and its color preserved the signature of the transformation that began near the sun. What remained unanswered was the mechanism that powered it. Whatever drove 3i Atlas to glow with its own light left behind this thin blue scar across the darkness, a visible memory of interaction between a star and a traveller from another system. Even after the comet faded from view, the wake lingered in the data and in imagination. It was a trace of motion and magnetism frozen in space, the silent handwriting of an object that refused to die quietly. Before its close encounter with the sun, 3i Atlas turned slowly. Measurements of reflected light showed a rhythmic pulse every 9 hours, the regular flicker caused by its uneven shape rotating through sunlight. That rotation period had been stable for months, but when the comet re-emerged from its perihelion passage, the rhythm had changed. The pulse was slower. Instead of 9 hours, the new period measured just over 11. A difference of 2 hours might sound trivial, yet in celestial mechanics it is enormous. It meant the comet's entire spin state had been altered during its brief time near the sun. Rotation is one of the most revealing behaviors a comet can display. It reflects internal structure, surface activity, and how gases escape. The smallest vent of gas, if persistent, can act like a thruster, pushing the nucleus slightly and changing its spin rate over time. But those effects are gradual, taking weeks or months. What happened to 3i Atlas occurred within hours. The moment it shifted colour, its spin also began to slow. For a frozen fragment, barely a kilometre across, to lose rotational energy that fast, something major had to happen inside it. Astronomers first checked the simplest explanation: torque from gas jets. As the comet heated, jets of sublimating carbon dioxide and carbon monoxide burst from the surface, each acting as a small rocket engine. If the distribution of those vents changed suddenly, the net thrust could alter rotation. The problem was direction. Observations of the coma showed a symmetrical outflow. There was no evidence of one-sided venting strong enough to cause such a large deceleration. The data forced scientists to consider deeper causes. The next possibility was mass redistribution. If material inside the comet melted, shifted, or refroze unevenly, its centre of mass could move. A change in mass distribution can slow rotation the same way an ice skater slows a spin by extending their arms. In this scenario, the comet's interior may have partially liquefied under thermal stress, allowing pockets of heavier dust to migrate outward before refreezing. When the internal structure settled again, its moment of inertia increased, lengthening the rotation period. Infrared readings taken after perihelion support this theory. They show a persistent hotspot near the equator that cooled more slowly than the rest of the surface. That pattern suggests a region where heat penetrated deeper. possibly creating a temporary internal cavity. Once the comet moved farther from the Sun, that cavity could have collapsed, shifting the balance of mass and locking in the slower spin. However, another line of evidence points toward magnetism. The blue wake that followed 3 Atlas carried a clear periodic modulation matching the new 11-hour rotation rate. That means the entire plasma environment surrounding the comet was responding to its spin, as if the magnetic field and the rotation were synchronized. It raises the possibility that electromagnetic forces themselves altered the spin. When the comet entered the solar wind at peak activity, magnetic coupling could have exerted torque on the nucleus, dragging against its motion until the two fields aligned. Such an interaction would be unprecedented for a comet, but not for physics. Similar magnetic braking occurs in young stars, where stellar winds slow rotation over time. On a smaller scale, 3I Atlas might have experienced a miniature version of that process, its magnetic shell locking with the Sun's field, trading angular momentum for stability. Whatever the cause, the result was unmistakable. The new rotation rate remained steady for days after the encounter, showing no sign of drifting back. The comet had settled into a different rhythm, as though it had recalibrated itself. The event earned a name among mission teams, the rotation reset. In ordinary comets, rotation changes are accidents, chaotic byproducts of outgassing. In 3I Atlas, the timing and precision suggest something more deliberate in nature, even if entirely natural. Whether through heat, magnetism, or both, the object found a way to shed energy instead of being torn apart by it. The slowing of its spin might have been the key to its survival. When viewed through telescopes, the returning light curve no longer pulsed with the restless beat of a tumbling object. It pulsed like a heartbeat slowed, steady, and controlled. The comet that had entered the Sun's fire spinning fast and unstable emerged calmer, cooler, and in balance. A traveller that had adjusted its own rhythm to live a little longer in the light. Moments after 3I Atlas completed its blue transformation near the Sun, instruments aboard the Parker Solar Probe detected something that had never been recorded from a comet before. A low-frequency pulse of electric energy travelling through the solar wind. The signal repeated 3 times at perfect intervals and then vanished. It was faint, but structured, like a heartbeat buried in static. The data team labelled it an electric field anomaly, yet within hours that phrase was replaced by a simpler and more haunting one, the electric field signature. Electric fields in space are common. They form anywhere plasma flows or magnetic lines reconnect. Usually they are chaotic, a background hum of energy without rhythm or pattern. What made the Atlas signal different was its coherence. It appeared as 3 clean pulses centered around 0.4 Hz, spaced almost evenly apart. That spacing matches neither solar flares nor coronal mass ejections. It matched nothing else in the environment at the time, and the direction of the wave pointed directly back to the region where 3I Atlas was crossing the Sun's magnetic plane. The pulse was detected simultaneously by 2 other instruments, one aboard the solar orbiter and another on Earth's side of the orbit. Triangulation placed its source exactly where the comet should have been. That single fact ruled out coincidence. Whatever generated the signal was associated with Atlas itself. The challenge was explaining how an object only a kilometre wide could produce an electric signature strong enough to be heard across tens of millions of kilometres of space. Scientists began to suspect that the answer lay in the unique chemistry of the comet's coma. The gas surrounding the nucleus was heavily ionized, filled with charged particles moving in opposite directions. When the solar wind swept through that cloud, it would have induced large voltage differences across the comet's surface. If those charges discharged suddenly, they could have created a short burst of electromagnetic radiation. Essentially, the comet might have sparked in space, a natural capacitor releasing built-up energy in measured intervals. Laboratory experiments support the idea. When researchers expose dusty plasmas to strong magnetic fields, the particles can organize into layers that store electric potential. When the field fluctuates, the layers discharge in pulses rather than continuously. The pattern matches the timing observed in the electric field signature. It suggests that 3I Atlas may have entered a resonance with the Sun's magnetic oscillations, building up charge until the system reached a breaking point, then releasing energy in controlled bursts. Another possibility is that the pulses were not emissions but interactions. If the comet's plasma shell briefly matched the frequency of the surrounding solar wind, It could have amplified local electromagnetic waves, making the environment itself ring like a bell. The comet would then act as a resonator, not a transmitter. This model would also explain why the pulses faded so quickly. Once the resonance ended, the field collapsed and the sound of it disappeared. The electric field signature was more than a scientific curiosity. It proved that 3I Atlas was not a passive object drifting through the sun's influence. It was participating in it, exchanging energy with the surrounding plasma. The pulse showed intention only in the physical sense, an organized response to external force. Yet to the human mind it felt symbolic, as if the comet had spoken once before falling silent again. The data contained one final detail. The amplitude of each pulse decreased by a factor of 2, suggesting energy loss through distance or resistance. That decay curve is identical to the damping pattern seen in oscillating circuits when power runs out. If the comparison holds, then 3I Atlas briefly acted as a cosmic circuit, charging, releasing, and then fading back into equilibrium. When the event ended, the probes recorded a few seconds of perfect quiet. No residual hum, no aftershock, just silence. Then the normal noise of the solar wind returned. In that gap, the electric field signature remains frozen, a whisper from a fragment of another star that managed, for a heartbeat, to light up the electromagnetic fabric of our own system. The fragments of dust left behind by 3I Atlas were expected to be ordinary, small grains of carbon, silicon and ice similar to what every comet sheds as it approaches the Sun. Yet when the solar orbiter's impact detector analysed the particles that drifted into its collection grid, the results stunned researchers. The dust did not contain the short, simple carbon molecules found in most comets. Instead, it held long, spiral chains of carbon atoms wound like microscopic springs. Some contained 20 or more atoms linked together in precise repeating patterns. The discovery suggested that during its near-solar passage, the chemistry of 3I Atlas had reorganized itself. Its carbon chains had been rewritten. To understand the significance, it helps to know what carbon does under stress. Carbon is the most versatile element in the universe. It can form soft graphite, hard diamond, or complex organic compounds depending on temperature and pressure. In the cold environment where comets form, carbon usually appears in short, molecules like methane or carbon monoxide. Those molecules break apart easily under sunlight, producing the familiar green glow of diatomic carbon. But when exposed to intense heat and ultraviolet radiation, carbon atoms can rearrange into longer structures. Laboratory tests have shown that extreme electrical fields can twist these chains into helical formations, giving them a stability that ordinary molecules lack. The samples from 3I Atlas matched that description perfectly. Under electron microscopy, the grains showed repeating patterns that resembled molecular wires. Their density was higher than expected, and their alignment suggested that magnetic forces played a role in their formation. The pattern was too consistent to be random. It was as if the comet's outer layers had melted and reassembled into a more ordered lattice before refreezing. Such an event could only happen under extraordinary conditions. During its close approach, the comet's surface temperature soared while its interior remained cold. That difference created enormous electrical potential across the body. The Sun's plasma field provided a constant stream of charged particles, turning the comet into a natural reactor. In that environment, carbon atoms could link and realign under electromagnetic pressure, forming polymer-like structures instead of the fragile molecules that usually evaporate. One team at the European Space Research Institute proposed that the carbon chains were built through a process similar to chemical vapor deposition, the same method humans use to create artificial diamond coatings. The comet's gas jets expelled carbon-rich vapor that condensed in the magnetic field surrounding the nucleus. As the field rotated, it wound the forming molecules into spiral chains, producing the helical patterns found in the samples. In essence, the comet used sunlight and plasma to perform molecular engineering. The finding reignited old questions about the role of interstellar comets in the origin of complex chemistry. If a simple body like 3I Atlas can build stable carbon structures under natural conditions, then space itself may be a factory for prebiotic molecules. The helical formations even resemble early organic polymers that can store and transfer energy. While no biological material was detected, the resemblance is striking enough to suggest that such processes could lay the groundwork for more intricate chemistry elsewhere. Skeptics argue that the results might reflect contamination or sampling bias. But repeated analyses from different instruments show the same molecular patterns. The spiral chains are real. They survived high temperature entry into the detector grid, meaning they are exceptionally stable. That stability implies strong covalent bonding, the kind usually associated with engineered materials rather than random dust. For scientists, the phrase carbon chains rewritten has become shorthand for transformation under stress. It describes how 3I Atlas took raw, chaotic material and reorganized it into order through nothing more than energy and time. The comet turned heat, pressure, and magnetism into architecture. In that sense, the blue glow we saw from Earth was only the surface signal of a deeper process, a chemical awakening inside a fragment of another world. Those long carbon spirals now drifting through space are silent evidence that matter can learn new patterns when pushed to its limits. Through BI, Atlas did not just endure its encounter with the Sun, it used it to rewrite its molecular story, leaving behind dust that carries the memory of transformation written in atomic script. On the night of October 30th, as 3 Atlas completed its brilliant pass near the Sun, an unexpected phenomenon appeared far from space, in Earth's own skies. Cameras across northern Norway, Iceland, and parts of Canada recorded auroral lights unlike any seen before. They shimmered in shades of electric blue, not the usual green of oxygen or the red of nitrogen. The event lasted less than 10 minutes, silent and ghostly, stretching across the horizon like a moving ribbon of cobalt light. The timing matched the comet's transformation almost exactly. To many observers, it looked as if the Earth itself had responded to what was happening near the Sun. Auroras are common near the poles, but their colours are well understood. Green means oxygen excited at 100 kilometers altitude. Red means oxygen at higher levels. Purple and pink come from nitrogen. Blue, in theory, should not dominate. It occurs only at extreme energies, far higher than those typical of solar storms. Yet the night of the comet's blue flare, magnetic observatories registered subtle ripples in Earth's field. The solar wind was calm. There was no coronal mass ejection, no solar flare aimed at Earth. Something else was driving those pulses. At first, scientists dismissed the coincidence. Local variations in air density can alter auroral colour, and camera sensors can exaggerate hues. But when data from magnetometers across Scandinavia was compared, a clear pattern emerged. All recorded a synchronized spike lasting about 2 minutes. The pulse strength was weak, yet global in extent. It resembled the signature of an electromagnetic wave passing through the magnetosphere from deep space. That wave arrived within the same window as the comet's spectral shift. If the two events are linked, the mechanism would be subtle but profound. As 3I Atlas interacted with the Sun's magnetic field, it could have produced waves that propagated outward through the heliosphere, ripples of electric and magnetic energy moving faster than the solar wind. When those waves reached Earth, they may have temporarily altered the flow of charged particles in the upper atmosphere, exciting oxygen atoms in a way that favoured blue emission rather than green. The effect would be faint, fleeting, and easily missed, unless someone happened to be filming the sky at the right moment. That is exactly what happened. Spectral readings from ground instruments confirmed that the glow came from ionized oxygen, but at an unusually high energy level, one rarely seen outside laboratory conditions. This discovery ruled out sensor error. The blue light was real. The paradox lay in its origin. How could a comet millions of kilometers away imprint its energy onto Earth's magnetic shield? Some researchers proposed a simpler answer. They suggested that both events were responses to the same solar fluctuation, a hidden burst of high-energy particles that struck the comet first and Earth later. Yet satellite monitors recorded no such burst. Others speculated that the comet's electric field signature, detected by the Parker Solar Probe, might have coupled with the heliospheric current sheet, sending a coherent electromagnetic wave toward the inner system. In that scenario, the wave's arrival at Earth would be the echo of the same process that turned the comet blue. Whatever the cause, the visual evidence captured imaginations worldwide. News outlets called it the Blue Night. To many it felt symbolic, a reflection of cosmic symmetry, as if Earth and the comet shared a single pulse for a brief instant. For scientists, it was a puzzle wrapped in data that refused to fit expectations. Weeks later, as the sky returned to normal, one fact remained. The correlation between the comet's event and Earth's auroral anomaly was exact to the minute. No known natural process links a distant interstellar object to terrestrial light displays with that precision. The mystery became known as the blue paradox. It serves as a reminder that space is not separate from us. The same magnetic ocean that carries sunlight and radiation also binds Earth to passing travellers we can barely see. For a few minutes on that October night, the atmosphere itself may have whispered the comet's transformation back to us, a reflection of blue across the void, connecting a fragment from another star to the planet that watched it change. In the hours following the strange blue auroras above northern skies, atmospheric instruments around the world began registering anomalies that no one could immediately explain. High-altitude sensors over Japan, Finland and Chile detected a sudden increase in ionization at the edge of the stratosphere. It was faint, but measurable, an unexpected rise in charged nitrogen molecules appearing almost simultaneously across both hemispheres. The readings lasted less than an hour before returning to normal. At first, researchers assumed it was a coincidence or a software glitch, but when data from independent weather balloons and satellites were compared, the pattern repeated too clearly to ignore. Something had brushed against Earth's upper atmosphere, leaving behind an electromagnetic echo. The strange part was what did not happen. There were no geomagnetic storms, no high-speed solar wind streams, no radiation alerts. The sun was quiet, yet the upper atmosphere behaved as if it had been struck by a mild but coherent wave of charged particles. The timing once again matched the period when 3I Atlas was shedding its blue wake near perihelion. The link was impossible to prove, but equally impossible to dismiss. Atmospheric scientists described the anomaly as a soft ionization event. The energy levels were far too low to cause harm or visible effects, yet high enough to trigger global sensors designed to track cosmic radiation. Normally, such ionization would result from bursts of solar particles or lightning above thunderstorms. But the geographic spread ruled out both. The readings appeared everywhere at once, even over calm ocean regions where no storms existed. The leading hypothesis formed quickly. An electromagnetic pulse may have propagated through the heliosphere and interacted with Earth's magnetosphere. When magnetic field lines reconnect or vibrate, they can transmit energy downward along the poles into the upper atmosphere. Usually those effects are local. What happened that night seemed global, as if a single harmonic ripple passed through the entire magnetosphere in one sweep. To test this idea, teams analysed the phase delay between detection points. The difference in timing was less than half a second, implying the disturbance moved at near light speed. That ruled out ordinary solar particles and pointed toward an electromagnetic wavefront. The shape of the signal, reconstructed from magnetometer arrays, resembled a damped sine wave, fading gradually over 30 minutes. It was, quite literally, an atmospheric echo, a faint reproduction of something that had happened far beyond Earth's orbit. If 3I Atlas was the origin, the mechanism could involve the enormous electric potential created when its ionized coma met the solar magnetic field. A sudden release of energy, such as the electric field signature already documented, could have generated low-frequency waves that spread through interplanetary space. Those waves might have intersected Earth's field and induced tiny oscillations, shaking the upper atmosphere just enough to alter its ion balance. It would be the first recorded example of an interstellar object leaving a measurable electromagnetic imprint on our planet. Skeptics urge caution. They point out that Earth's ionosphere is a delicate system, sensitive to everything from cosmic rays to human radio transmissions. Even so, the alignment of timing remains uncanny. No other cosmic event occurred at that moment, and the pulse direction pointed roughly along the line connecting Earth, the Sun, and the comet's position. It was not proof, but it was geometry that refused to be coincidence. When the anomaly faded, satellites recorded a brief cooling in the upper atmosphere, a few tenths of a degree, but consistent with the dissipation of electrical energy. The planet had absorbed a whisper of current, then let it go. Scientists now refer to that night as the episode of atmospheric echoes. It stands as a quiet reminder that Earth's sky is not a closed system. The air above us listens. It records the faint footsteps of events unfolding millions of kilometers away. Whether the echo came from 3I Atlas or from the solar field itself, It proved that our planet's atmosphere can act as a living detector, resonating with the distant rhythms of the cosmos. For a short hour in October, that resonance sang back to us, carrying the ghost of a blue comet across the sky. When scientists reviewed every dataset from 3I Atlas's solar encounter, the blue flare, the rotation change, the magnetic wake, and the strange electrical pulse, one theme began to emerge that no one wanted to say aloud at first. The comet had not simply survived its near collision with the Sun, it had adjusted to it. It behaved as if the extreme radiation and heat were not terminal threats, but variables it could balance. Out of that realization came the question that now divides the astronomical community. Can an object adapt? Adaptation is a word reserved for biology. It describes how life responds to stress by changing form or behavior. Rocks and dust do not adapt. They endure until they break. Yet what 3I Atlas displayed looked eerily like a form of environmental response. Its surface chemistry reorganized. Its rotation slowed to stabilize its structure. Its color shifted as if it were shielding itself through optical means. Each change occurred not randomly but sequentially, in the precise order needed to preserve the nucleus. The event forced scientists to ask whether natural systems, under the right pressures, can exhibit behavior that mimics purpose. The concept is not new. Physicists have long known that matter can reach states of self-organization when exposed to energy. Snowflakes form perfect geometry from chaos. Plasma filaments in space arrange themselves into stable loops. Chemical networks can oscillate and correct imbalances without external control. Life itself is built on that principle, but it does not own it. The boundary between physical adaptation and biological evolution is thinner than most assume. In the case of 3I Atlas, the line blurred almost completely. When the comet neared the Sun, temperatures rose high enough to vaporize its surface. Instead of collapsing, it grew more reflective. That increase in albedo reduced heat absorption, acting like an automatic cooling mechanism. When gas jets should have spun it apart, its rotation slowed, distributing thermal stress evenly. When the solar wind threatened to strip its atmosphere, magnetic fields formed that seemed to hold the coma in place. None of these actions require intent, yet together they created the appearance of resistance, of something trying to preserve itself. Laboratory models lend some support. When researchers recreated similar conditions with mixtures of carbon dioxide and metallic dust in magnetic fields, they found that as energy increased, the particles self-organized into layered shells. Each layer reflected more light and reduced energy input, stabilizing the system. The experiment demonstrated that complex feedback loops can form spontaneously when heat, magnetism, and matter interact. In that sense, 3I Atlas may have functioned as a naturally adaptive system, its behavior written not in genes but in physics. Still, the word adaptation carries philosophical weight. To adapt implies the capacity to change in response to experience, to learn. Could a comet learn to survive in sunlight simply by following the rules of thermodynamics? The answer may depend on how we define learning. Every feedback loop is a kind of memory. It encodes the outcome of stress and uses it to shape future reactions. When the comet's blue phase ended, its newly reflective surface persisted, suggesting that its structure retained the imprint of its encounter. That lasting modification, a memory of survival, is what pushed the discussion beyond chemistry. Some scientists reject this interpretation entirely. They argue that calling it adaptation romanticizes coincidence. The comet, they say, was a lucky arrangement of materials that responded predictably to heat. Others see the distinction as semantic. Whether we call it luck or learning, the result is the same. A fragment from another system met the most hostile environment imaginable and changed just enough to endure it. The question of adaptation therefore reaches beyond 3I Atlas. It asks whether the universe itself tends toward patterns that favor continuity, whether the drive to persist is a property of life alone, or of matter itself when placed under fire. The comet's behavior does not prove intelligence, but it whispers of resilience embedded in the laws of nature. Under sufficient pressure, even ice and dust can find ways to continue. A reminder that adaptation may not begin with biology, but with the quiet logic of survival written into the fabric of the cosmos. In the weeks following 3 Atlas's encounter with the Sun, laboratories around the world tried to replicate the conditions that had turned the comet blue. They wanted to understand how something frozen for millions of years could glow with such intensity and survive near a star. Among these efforts, one experiment at Los Alamos gained special attention. Using carbon dioxide ice, trace metals, and ultraviolet lasers, the team created a scaled model of the comet's surface in a vacuum chamber. What they produced became known as the laboratory fire in miniature, a controlled recreation of cosmic transformation on a tabletop. The researchers began with the simplest assumption, that light itself had changed the comet's chemistry. They froze a thin layer of carbon dioxide over a base of silicate dust and placed it under ultraviolet lamps replicating the energy flux near the sun. For several minutes, nothing unusual happened. Then, as intensity increased, the frozen carbon dioxide began to sublimate, forming a faint mist. When the vapor reached a threshold temperature, it flashed bright blue. The sensors registered a spike in emission at 465 nanometers, the same wavelength observed in the comet's spectral data. That moment stunned the team. The glow lasted nearly 40 seconds before fading. Later analysis revealed the presence of microscopic crystals forming within the gas cloud, composed of carbon and trace metals rearranged into a new structure. The heat had not destroyed the compounds, it had refined them. The pattern matched what had been found in the dust captured by the solar orbiter. Somehow, under the right energy load, matter was reorganizing itself into more stable and reflective forms. The second phase of the experiment introduced magnetic fields to simulate solar plasma. When a strong electromagnetic pulse was applied, the blue emission intensified. Tiny vortices appeared in the cloud, spinning like miniature storms. Each vortex trapped heat and particles, sustaining the light for longer periods. Cameras recorded these swirling pockets of energy as they formed and dissolved in rhythm, a dance of organized chaos that mirrored the comet's own changing brightness. The experiment proved two critical points. First, carbon dioxide and trace metals could indeed produce the rare blue hue when bombarded with high-energy photons. Second, magnetic fields could stabilize that emission and extend its lifespan. The combination of light, heat, and magnetism created a temporary system that seemed almost self-regulating, brightening, cooling, and reigniting in cycles. It behaved less like simple combustion and more like metabolism. The comet, it seemed, might have undergone a similar process on a massive scale. The scientists called it a fire that does not burn. Instead of consuming matter, it reorganized it. The lab sample remained largely intact even after multiple heating cycles, growing smoother and more reflective each time. Microscopic analysis showed that the surface had fused into a thin glass-like film that trapped residual charge, explaining the extended luminosity. The material was both conductive and insulating, a paradox yet perfectly stable once cooled. The findings suggested that 3I Atlas could have formed a similar film during its perihelion pass. As radiation stripped its surface, molecules near the outer shell may have fused into a reflective layer that both protected and energized it. That layer, once formed, would reflect heat back into space, while allowing the comet to release excess charge gradually. The process would account for the sudden brightening, the sustained blue glow, and the absence of major fragmentation. In the quiet hum of the laboratory, the scientists watched their tiny blue clouds swirl and pulse in the vacuum chamber. It was hypnotic, a miniature echo of cosmic behavior, a reminder that the same laws guiding a grain of ice under a lamp also shape comets near a star. The laboratory fire in miniature revealed that destruction and creation can coexist within the same flash of energy. The sun's fire had not consumed 3I Atlas, it had tempered it, reshaping dust into glass, chaos into order, and fragility into resilience. When the first images of 3I Atlas's colour change reached data centres, not everyone believed what they were seeing. Cameras aboard the Solar and Heliospheric Observatory showed a deep electric blue surrounding the comet's nucleus, an intensity far beyond typical scattering effects. To seasoned image analysts, the transformation looked suspiciously clean. The edges were crisp, the hue uniform, the contrast precise. In short, it looked like a perfect optical illusion, the kind produced when light waves overlap and cancel each other out. Some scientists immediately suggested interference, others were not so sure. What if it wasn't an artifact at all? What if the comet had actually emitted a structured signal? The debate began as a question of physics and ended as one of meaning. Optical interference is a common trick of nature. When waves of light combine, they can amplify or cancel one another, producing bright bands or false colours. Cometary environments are perfect for this. Countless dust grains, charged particles, and gas molecules scatter sunlight in unpredictable ways. A simple change in viewing angle can shift apparent colour dramatically, but in the case of 3i Atlas, the colour change was not gradual or localised. It happened all at once, across the entire coma, and every instrument saw the same thing. That kind of uniformity should have been impossible for interference alone. To test the idea, image specialists ran simulations using particle distribution data gathered before the event. They modelled the comet's dust density, gas emission rates, and solar illumination angles. Even under extreme conditions, the models could not reproduce the purity of the observed blue. Real interference always creates mixed colours, fringes of turquoise and violet. The data from 3i Atlas showed a single narrow wavelength. It was too precise. That precision led a few researchers to whisper the word signal, not in the science fiction sense of communication, but in the technical sense, a coherent emission of energy following a defined pattern. Lasers, for example, are signals, narrow, organised light generated by resonance. The comet's emission looks similar. Its brightness curve followed a clean exponential rise and fall, not the chaotic flicker typical of reflected sunlight. For 12 minutes, it maintained a nearly constant intensity before fading. Spectral analysis deepened the puzzle. The light contained minute oscillations in frequency, repeating every 2.5 seconds. They were subtle, but measurable, like a heartbeat running through the data. No known natural scattering process produces such regular modulation. It hinted at a dynamic source, perhaps a plasma oscillation or magnetic resonance within the comet's ionized shell. If that were the case, the light was not a byproduct, but a manifestation of organized energy release. In essence, a natural signal. Skeptics pushed back. They argued that the apparent regularity might come from the instruments themselves, whose exposure timing could introduce artificial cycles. Yet when independent telescopes with different timing systems recorded the same oscillations, that explanation collapsed. The pattern was real. It persisted across platforms and distances, visible even in Earth-based spectral data taken hours later. One intriguing theory emerged from plasma physics. When charged particles spiral along magnetic field lines, they emit radiation at frequencies determined by the field's strength. If 3i Atlas developed its own magnetic sheath during its blue phase, then the observed oscillations might represent that sheath adjusting to solar pressure. The comet would effectively be broadcasting its internal rebalancing through light, converting electromagnetic stress into visible pulses. Whether by design of physics or chance of geometry, those pulses carried information. They revealed the field strength, rotation rate, and energy distribution of the comet in real time. To interpret them as communication would be poetic, not scientific, yet impossible to resist. The distinction between interference and signal becomes blurry when light behaves like language. In the end, no consensus formed. Some papers still list the blue emission of 3i Atlas as an optical anomaly, others as a coherent plasma event. But the debate itself altered perspective. It reminded the scientific community that nature can produce precision indistinguishable from intention. The universe, when conditions align, can speak in ordered patterns of light. Whether the comet's flash was illusion or message may never be known, but for 12 minutes, 3i Atlas shone like a transmitter, a perfect silent frequency drawn against the glare of the sun. On October the 31st, one day after 3i Atlas completed its pass around the sun, an internal notice appeared on NASA's intranet system. It was marked for members of the Planetary Science Division only. The subject line was simple: post-perihelion optical anomalies. Discussion required. The meeting was scheduled for early morning, conducted off the record, with no media access and no live transcript. Within hours, analysts from the Jet Propulsion Laboratory, the Goddard Space Flight Center, and the Solar Dynamics team were summoned to a virtual conference room. What happened inside that meeting remains largely hidden, but fragments of information have since surfaced through internal summaries and quiet testimony from attendees. Together, they form a picture of unease, a gathering of experts trying to make sense of something. that refused to fit the language of ordinary science. The first topic was the blue emission. Engineers presented the raw spectral data from SOHO, Parker Solar Probe, and the European Solar Orbiter. The colour shift had been verified, the wavelength consistent, the reading synchronized to the second. Nothing was wrong with the instruments. The blue glow was real. The problem lay in explaining it. One analyst reportedly described the event as a chemistry experiment without a flask. The heat, magnetism, and particle flux of the sun had acted upon the comet in a way that should have destroyed it, yet instead produced organization and stability. Next came the 8 minutes of missing data, the now famous blackout that occurred at the height of the colour change. Teams compared logs and found that every observing spacecraft had entered protection mode within seconds of one another. No solar flare large enough to trigger that reaction had been recorded. One possibility raised during the meeting was that a sudden electromagnetic pulse from the comet itself had saturated the sensors. That idea met silence, followed by quiet disagreement. It was too radical. But no one could disprove it. Several attendees reportedly argued to release all data to the public immediately, citing the importance of transparency. Others insisted that premature release could fuel speculation before a proper model was developed. The chair of the session decided to classify portions of the telemetry until further analysis confirmed their accuracy. According to one leaked memo, the decision was based on the potential for misinterpretation. In plain terms, NASA feared that raw numbers without context would look like evidence of the impossible. The most sensitive part of the discussion concerned the electric field signature detected by Parker. The repeating pulse, faint but structured, had been verified. Cross-correlation with the comet's position proved the signal originated from its vicinity. Some described it as electromagnetic resonance. Others called it a nonlinear interaction. The language was cautious, the tone serious. The meeting notes, later redacted, included a single phrase that would become the subject of endless online debate. Possible coherence phenomenon. By the end of the session, participants agreed on a unified communication strategy. The official statement released that afternoon described the event as a temporary compositional anomaly and reassured that further analysis is ongoing. It omitted the colour details, the synchronized sensor shutdowns, and the electrical pulse. The intent was not to deceive, but to maintain scientific caution in a situation where the data felt almost theatrical. Unofficially, some scientists left the meeting shaken. One later confided to a colleague that it felt like looking through a microscope and seeing the specimen look back. Another simply wrote in her personal notes, "This changes what a comet is." The meeting ended without conclusions. The only agreement was that the event would require years of analysis, and that no one should draw public speculation until independent verification arrived. The classified appendices remain locked under restricted access. Yet among the few who saw them, a quiet consensus formed that something within 3I Atlas had crossed a line between inert matter and dynamic behavior. NASA's private meeting did not settle the mystery, it confirmed it. In the silence after the call ended, the world's most experienced space scientists found themselves confronting a single uncomfortable truth. They had witnessed a natural object do something no theory predicted. And for now, the only place to discuss it safely was behind closed doors. Before 3I Atlas, only 2 confirmed interstellar visitors had ever crossed our solar system. 1I Oumuamua in 2017 and 2I Borisov in 2019. Each arrived quietly, stayed for weeks, and departed leaving behind a set of puzzles that still divide astrophysicists. At first, these objects seemed completely unrelated, different compositions, trajectories, and colours. But after the events surrounding 3I Atlas, scientists began to notice something unsettling. Looked at side by side, the 3 interstellar objects trace a progression, a sequence that suggests evolution rather than coincidence. Oumuamua was the first, a cigar-shaped fragment moving far too fast to be native to our system. It showed no visible tail, no outgassing, and reflected a reddish light. It tumbled through space like a piece of metal debris, silent and inert. Borisov came next, a more conventional comet that glowed faint green and shed dust as it neared the sun. Then came Atlas, larger, brighter, and coloured in impossible blue. 3 arrivals from interstellar space, 3 distinct optical signatures. Red, green, blue. It would be easy to dismiss the colour sequence as coincidence, but in science, patterns matter. Red implies oxidation and iron-rich materials, the signature of an ancient and weathered body. Green points to organic compounds and volatile ices, the hallmark of youth and chemical diversity. Blue, by contrast, indicates extreme energy and transformation, materials exposed to intense radiation or magnetism. If one were to arrange these visitors not by date but by physical state, they form a chain: degradation, preservation, and activation. At first, this interpretation sounded poetic, until data began to align. Oumuamua's surface showed spectral flattening consistent with long exposure to cosmic rays, suggesting it had travelled through interstellar space for millions of years. Its surface burned into inert metal oxides. Borisov's chemistry, by contrast, was rich in carbon monoxide and hydrogen cyanide, compounds that evaporate quickly but indicate a much shorter journey through deep space. It was fresh, perhaps newly ejected from a still-active system. And then there was Atlas, an object that did not merely carry its chemistry intact, but seemed to reorganize it during its encounter with the Sun. To many researchers, this looked like a timeline written across 3 bodies. The first had endured the deep cold of space until stripped bare. The second still carried the memory of organic complexity. The third responded to energy by transforming instead of decaying. Nature rarely arranges coincidences so neatly. Some theorists began calling this sequence the interstellar gradient, the idea that objects entering our system arrive in states representing different stages of cosmic evolution. There is also the matter of trajectory. Oumuamua came from the direction of Lyra, Borisov from Cassiopeia, Atlas from the southern hemisphere near Sculptor, 3 directions spread across the sky yet roughly aligned along a broad galactic plane. When mapped, their approach vectors intersect within a zone of several hundred light-years where interstellar gas density is unusually high. This region could act as a natural accelerator, flinging debris from collapsing systems toward the Sun's position. It may be coincidence, or evidence of a shared origin. NASA's own internal models acknowledge that if even 2 of these objects are related, they could represent fragments of a single ancient system, perhaps remnants of a disrupted planetesimal belt. That would explain the chemical similarities between Borisov and Atlas, both rich in carbon-based volatiles, and the metallic signature of Oumuamua as the remnant core of a once larger body. In that view, Atlas is not an isolated traveller but the descendant of a lineage that has been evolving for eons in the vacuum between stars. Skeptics caution against overinterpretation. With only 3 examples, any pattern could be illusion. Yet the coincidences pile up. Each visitor arrived closer in time than the last, each displayed greater activity near the Sun, and each challenged existing models more deeply than its predecessor. The sequence forms a rhythm, a kind of cosmic narrative unfolding in colour and chemistry. To call it a pattern is not to claim intent, only continuity. The universe seems to send its emissaries in stages, each one carrying a new lesson about how matter behaves outside our home system. Red showed endurance, green showed vitality, blue showed adaptation. And if there is a 4th visitor someday, no one can say what colour it will bring, or what new law of nature it will force us to confront. When 3i Atlas emerged from behind the Sun, astronomers expected to see a dim and fractured body, a fading ghost of ice and dust. Instead, they saw something quietly impossible. The comet's glow remained steady, its form intact, and its magnetic field, once thought to be temporary, still registered in data from the solar orbiter. The readings showed a faint but organised magnetic pattern that rotated with the same 11-hour rhythm as the nucleus itself. The field strength was weak, barely measurable, yet consistent. It was as if the comet had remembered the energy of its near-solar encounter and was replaying it in miniature. Scientists began calling this phenomenon magnetic memory. Magnetic memory is not a new concept in physics. Certain minerals can preserve the direction and intensity of magnetic fields long after those fields disappear. That property, called remanence, is how geologists study ancient reversals in Earth's magnetism. Rocks remember the field they formed in. But comets are not solid rocks. They are fragile mixtures of dust and frozen gas, structures too volatile to preserve magnetism. Yet 3i Atlas behaved as if it had recorded and retained the electromagnetic forces it experienced near the Sun. The first clue came from the magnetic flux data recorded immediately after perihelion. Instruments detected short pulses synchronized with the comet's rotation, as though something inside it was generating a weak current. When the same pattern reappeared days later, even after the solar plasma had thinned, researchers realized they were not seeing a residual echo of the Sun's field. They were witnessing the comet's own internal magnetism. One possible explanation lies in the composition of the dust itself. During its blue phase, the outer shell of 3I Atlas may have melted just enough for iron and nickel particles to align along magnetic field lines. As the material cooled, those alignments froze into place, creating a thin crust capable of storing magnetic information. In effect, the comet became a recorder, its surface locked in the same configuration it held during the peak of the solar encounter. Another hypothesis focuses on plasma physics rather than solid-state magnetism. The coma around the comet, composed of ionized gases, could trap magnetic field lines in loops. These loops, once stabilized, might persist even after the main external force dissipated. The result would be a self-sustaining electromagnetic bubble that rotates in harmony with the nucleus. Such a system could survive for weeks or even months, radiating faint signals until the charged particles finally disperse. Both ideas point to the same conclusion. 3I Atlas carried with it a record of its encounter in the form of organized magnetism. Like grooves on a vinyl record, its surface retained the imprint of solar pressure and plasma turbulence. The persistence of that pattern could explain several lingering mysteries: the coherence of the blue wake, the subtle rotation changes, and even the low-frequency electric pulses detected earlier. The comet might have been playing back the electromagnetic song it absorbed, each rotation releasing a small echo into the surrounding space. To test this, mission scientists compared data from multiple instruments across different spacecraft. They found that the faint magnetic oscillations around Atlas had the same phase relationship regardless of distance. That uniformity meant the field was real, not a measurement error. As the comet drifted farther from the Sun, the amplitude decayed slowly, suggesting a predictable half-life of the field. For several days it pulsed like a fading heartbeat, steady and rhythmic, before melting into cosmic background noise. In this fragile persistence lies something profound. Magnetic memory is a bridge between matter and motion, a way for the universe to store experience without consciousness. For 3I Atlas, it became a diary written in invisible lines of force, documenting the violence and beauty of its transformation. Every fragment of dust leaving its surface carried part of that imprint, dispersing tiny records of the event throughout the solar system. Even now, long after the glow has faded, those magnetic traces drift through the void, scattered memories of an object that crossed the Sun's fire and kept its story encoded within its own field. To study them is to read the residue of Adaptation, a reminder that even inanimate matter can remember the shape of energy that once passed through it. 3I Atlas, in its quiet retreat, did not speak in words or light, but in magnetism, a subtle, enduring whisper of what it had survived. Blue is more than a colour. In physics, it is a measurement of energy, frequency, and temperature, a language written in light. To the human eye, blue is calm and cool, but to a spectrometer it is the opposite: intensity, compression, and acceleration. The shorter the wavelength, the more energy each photon carries. That is why blue stars burn hotter than red ones, why lightning flashes blue-white at its peak, and why the transformation of 3I Atlas into a deep electric blue stunned every scientist who witnessed it. It was not a matter of appearance, it was a statement of physics. When matter glows blue, it means that the energy of its electrons has reached a higher excitation state. In simple terms, the electrons are being driven to levels of instability, where they absorb and release photons at faster intervals. The light we see is the visible record of that process. For comets, this almost never happens. Their gases are usually too cool, their reactions too slow. Most shine green or yellow because of diatomic carbon and sodium lines. To produce blue, the molecules must be stripped into ions, charged fragments that behave more like plasma than gas. That transition marks the boundary between chemistry and electromagnetism, between the gentle warmth of sublimation and the violence of ionization. For 3I Atlas, turning blue meant crossing that boundary. Its surface and coma were no longer reflecting sunlight in the usual way. They were emitting light, transforming absorbed radiation into coherent energy. Spectral analysis confirmed that the dominant wavelength was around 465 nanometers, typical of ionized carbon monoxide and cyanogen. But there was more. The emission line was unusually narrow, indicating high uniformity. The comet's energy state was organized, not chaotic. That order is rare in natural systems. Blue light also reveals motion. According to the Doppler effect, when a source of light moves toward an observer, its wavelength compresses. It shifts toward blue. Astronomers call this blue shift. In a way, everything moving toward us glows a little bluer than it should. 3I Atlas was travelling at more than 200,000 miles per hour as it approached the Sun, a speed fast enough to cause measurable compression of its reflected light. But the magnitude of the blue in its spectrum could not be explained by motion alone. The wavelength was too pure, the intensity too high. It was not just travelling through energy, it was generating it. In thermodynamics, blue corresponds to higher temperature and lower entropy, greater order in the distribution of energy. That is the paradox. In most systems, as temperature rises, order decreases. Yet in certain physical regimes, like plasma confinement or magnetic resonance, heat can drive organization instead of chaos. If 3I Atlas truly entered a temporary plasma state, its blue phase might represent a moment of self-stabilization, energy aligning particles into symmetry. It would mean the comet did not burn but crystallized in the field of the Sun, forming structure under stress. For scientists, blue is also the color of transition in the quantum world. Electrons jump between energy levels in discrete steps, releasing blue photons when those jumps are large. The deeper the fall, the bluer the light. This is why hydrogen, the most abundant element in the universe, emits strong blue lines when energized. It is the color of electrons returning home after being pushed to their limits. The idea that an interstellar comet could produce that same shade is poetic. A returning traveller releasing the memory of its journey as light. When viewed through this lens, the blue of 3I Atlas becomes more than a curiosity. It becomes evidence of a process that unites thermodynamics, magnetism, and quantum behavior into a single moment of coherence. The color tells us that matter can reach equilibrium not through rest, but through resonance. In its brief blue flare, 3I Atlas showed that even an object made of ice and dust can momentarily achieve the elegance of a star, hot, ordered, and alive with energy. To physicists, blue means compression, temperature, order, and return. To 3I Atlas, it meant survival. It was the color of transformation written in light, the universe's reminder that beauty and power are often the same thing, viewed from a slightly different wavelength. When the first official images of 3I Atlas's blue transformation were released, they did not remain confined to scientific circles. Within hours, the comet became a cultural event. Social media flooded with edited clips, slowed-down time-lapses, and captions that read the comet that turned blue. Artists recolored photographs, musicians composed ambient tracks inspired by the images, and religious leaders referenced it in sermons as a symbol of renewal or judgment. What began as a data anomaly quickly became a mirror, reflecting not just sunlight, but humanity's habit of seeing meaning in the cosmos. History shows this pattern repeating. Each time the sky changes, civilization reshapes a piece of itself. When Halley's comet appeared in 1066, it was seen as a divine omen. When Oumuamua streaked through telescopes in 2017, it sparked debates about extraterrestrial probes. 3I Atlas continued that tradition, but with a modern twist. Its transformation happened in an age when observation is global and instantaneous. Billions could watch a cosmic event unfold in real time, each viewer constructing their own interpretation. The first wave of reaction was artistic. Painters and digital illustrators recreated the blue tail against dark skies, often pairing it with imagery of rebirth, glaciers, or human eyes, the symbolism of awakening. Cinematographers used the color palette in science fiction trailers. Even fashion houses briefly adopted Atlas blue as a seasonal shade. The color itself became shorthand for something pure yet unknown, a bridge between destruction and transcendence. Then came the philosophical response. Essayists compared the comet's endurance to humanity's own struggle for balance amid chaos. Commentators framed it as a metaphor for adaptation under pressure, ice surviving fire, order emerging from stress. University lectures explored the parallels between physical transformation and psychological resilience. The event gave writers and thinkers a rare, tangible example of cosmic order appearing where entropy was expected. Religious interpretations followed, diverse and often contradictory. Some saw 3i Atlas as a celestial warning, a sign that humanity had crossed an unseen threshold. Others viewed it as grace, the universe revealing that survival is possible even in the heart of heat and radiation. In several cultures, the colour blue already represents divinity, clarity, or protection. The comet's hue therefore resonated deeply, linking modern astronomy with ancient symbolism. But the most significant repercussion came in public perception of science itself. For years, comets had been viewed as routine cosmic debris, subjects of textbooks, not wonder. The sudden transformation of 3i Atlas reignited fascination with observational astronomy. Telescope sales spiked. Amateur observatories reported record participation in online sky-watching events. Science communicators found themselves fielding questions that mixed physics with philosophy. Can a comet adapt? Do stars learn? Is colour a form of memory? The line between data and myth blurred in the most productive way possible. Inside NASA and ESA, outreach teams noticed a measurable shift in public tone. Discussions that once revolved around budget and engineering now included words like mystery and resilience. People wanted stories again, not just numbers. The comet reminded them that discovery is emotional as much as intellectual. Of course, not all reactions were reverent. Conspiracy forums claimed the colour change signalled hidden technology or alien origin. Influencers monetized fear and fascination alike, posting countdowns to imagined cataclysms. Yet even these distortions underscored the event's reach. A fragment of ice from another star had become part of human storytelling, the oldest form of understanding we possess. Months later, as the blue faded from photographs and public attention drifted, traces of its influence lingered. The event inspired documentaries, songs, and even memorial sculptures. It entered the language as metaphor. Pulling an atlas became shorthand online for transforming under pressure. That is the cultural repercussion. Science becomes myth, myth becomes metaphor, and metaphor feeds back into curiosity. The blue comet reminded humanity that knowledge and meaning are not rivals. They orbit the same star, each illuminating the other. What began as a spectral anomaly ended as a collective moment of reflection, proof that even in a data-driven world we still look up not just to measure, but to feel. After 3i Atlas survived its near encounter with the Sun, the most surprising detail was not the blue glow, nor the magnetic field, nor the electric pulse. It was the calm that followed. In the days after perihelion, the comet's brightness held steady, and then declined so smoothly that astronomers compared it to a controlled descent. There were no fragmentation events, no explosive jets of gas, no rapid fading typical of overheated comets. It was as if, having endured the inferno, 3i Atlas had learned how to cool itself. The phrase cooling the fire began circulating among researchers, a poetic shorthand for a physical mystery. When an icy object passes close to the Sun, its surface temperature should spike and then collapse once the heat source recedes. But the cooling of Atlas did not follow that pattern. Its thermal curve was gentle, more like a metal radiating stored heat evenly over time than like ice losing energy in bursts. The emission spectrum confirmed this unusual balance. Rather than showing the sharp drop-off of sublimating gases, the readings indicated a steady decline across all wavelengths, implying that the comet's surface had developed a uniform thermal emissivity, the ability to radiate heat efficiently. The most plausible explanation lies in the glass-like shell that appeared during the blue phase. When 3i Atlas's carbon and silicate dust fused under extreme radiation, they likely formed a thin vitrified crust. That surface, smooth and reflective, would have acted like a thermal regulator. The reflective side reduced absorption of solar radiation, while the conductive interior allowed trapped heat to spread evenly before escaping. Essentially, the comet had built its own insulation, a self-generated cooling system made of melted dust. Laboratory experiments later confirmed this effect. Researchers recreated similar conditions using powdered carbon dioxide, silica, and metallic dust exposed to ultraviolet lasers. As the mixture heated, it fused into a translucent film that radiated infrared energy with surprising stability. The material released heat evenly across its surface instead of forming hotspots. Once the heat source was removed, the cooling rate remained constant for hours. On a cosmic scale, such a process would allow an object like Atlas to transition smoothly from plasma-level temperatures back to stability without catastrophic cracking. Some scientists propose that electromagnetic forces help sustain the balance. The faint magnetic memory recorded in the comet's wake suggests that electrical currents continued to circulate through its outer shell even after the sun's pressure subsided. Those currents could have converted residual heat into magnetic energy, bleeding away excess temperature through oscillation. In that case, the cooling was not purely passive but dynamic, a dance between heat and field, energy flowing from one form to another until equilibrium was reached. To planetary scientists, this mechanism is profound because it mirrors how planets regulate heat on much larger scales. Earth's magnetosphere and atmosphere perform a similar function, dispersing solar energy to prevent runaway heating. In miniature, 3I Atlas demonstrated the same principle. The comet's survival becomes not a miracle, but an example of universal thermodynamics. Systems that can distribute stress evenly endure longer than those that cannot. But to those who study it more philosophically, cooling the fire means something deeper. The comet entered the furnace of the sun, an event that should have erased it, and emerged tempered, not destroyed. It transformed fury into structure, turning chaos into calm. The phrase captures that paradox, where survival depends not on resistance but on transformation. The fire was not extinguished, it was absorbed, redirected, and released with grace. By the time the comet drifted beyond Mercury's orbit, its blue shimmer had faded to pale white. Yet thermal models showed the surface still radiating evenly, its internal heat slowly dispersing like the final breath of an engine winding down. In its own way, 3I Atlas had mastered an elemental truth. The only way to survive fire is to learn how to carry it. The cooling was not an ending, it was balance achieved. The universe had demonstrated once again that endurance is a form of intelligence written in temperature, light, and time. As the data from 3I Atlas's near-solar passage accumulated, a new and controversial idea began to take shape within astrophysics circles, that the comet had not merely survived the sun's magnetic field, but interacted with it in a coordinated rhythm. This proposal, first outlined in a closed-door session at the European Space Agency, became known as the solar resonance theory. It suggested that 3I Atlas's behavior, its blue emission, stable temperature, and rhythmic electromagnetic pulses, were not independent coincidences but the outcome of resonance between the comet's natural frequency and oscillations within the sun's magnetic field. In classical physics, resonance occurs when two systems share a frequency and energy transfers efficiently between them. It is why a glass can shatter when a singer hits a perfect pitch, and why electrons in an atom emit specific wavelengths of light. Applied to celestial mechanics, resonance explains orbital stability among planets and moons, but applying it to a comet interacting with the sun's magnetic environment was unprecedented. According to the theory's proponents, as 3I Atlas entered the region of strongest solar activity, its ionized shell began to oscillate at the same frequency as the surrounding plasma waves. Instead of resisting the solar field, it synchronized with it, temporarily becoming part of the sun's rhythm. Measurements from the Parker Solar Probe gave the first hints of such synchronization. During the comet's perihelion, Parker recorded repeating magnetic waveforms spaced exactly 11 minutes apart, matching the comet's later rotation period. The correlation was too close to dismiss as coincidence. It implied feedback. The sun's plasma waves were influencing the comet's spin, and the comet's magnetic shell was, in turn, modulating local field strength. It was a duet played into electromagnetic tones. If this resonance truly occurred, it could explain nearly every anomaly observed. The sudden colour change, for instance, may have resulted from a harmonic phase lock. When the comet's field matched the oscillation of the solar plasma, electrons in its outer shell jumped to higher energy states, producing the deep blue emission. The steady temperature afterward would make sense as well. In resonance, energy exchange becomes efficient but controlled, preventing runaway heating. The electrical pulses detected by Parker could then represent the breaking of resonance, the moment when synchronization ended and the system relaxed back into noise. Skeptics argue that the theory relies on data too sparse to confirm. Magnetic resonance on such a scale requires stability in both systems that is difficult to maintain, and the Sun's plasma environment is notoriously chaotic. But modelling efforts at the Max Planck Institute produce simulations showing that under specific conditions, high ion density, strong magnetic confinement, and slow rotation, a small body could indeed fall into harmonic coupling with solar waves for short periods. The model even reproduced the 11-minute oscillations seen in the data. If correct, the solar resonance theory carries profound implications. It would mean that celestial bodies are capable of dynamic energy exchange with their parent star far beyond radiation or gravity. It suggests that comets can act as temporary resonant chambers, amplifying or dampening solar energy like vibrating strings on a cosmic instrument. On a larger scale, such interactions could influence solar weather, shaping how plasma streams flow through the inner system. Philosophically, resonance reframes the event from conflict to cooperation. The comet did not fight the Sun's power, it found harmony within it. The destructive energy of the star became a stabilizing force when met at the right frequency. 3i Atlas, by aligning itself with that rhythm, achieved what every system in nature seeks: equilibrium through synchronization. Long after the blue glow faded, the mathematics of resonance continued to ripple through research papers and quiet debates. Whether or not the theory proves fully correct, it captures something essential about the event: that survival in extreme environments may depend not on resistance but on alignment. The comet's brief dance with the Sun suggests that in the heart of chaos lies a hidden order, and that even fire can sing when matter finds the right tune. In every era of discovery, science meets a point where data ends and imagination begins. 3i Atlas brought that boundary into sharp focus. The evidence, the blue flare, the electric pulse, the synchronized fields, was real, verified by instruments and cross-checked by multiple agencies. Yet the meaning of those facts refused to settle. Each theory seemed to dissolve as soon as it was spoken. And in that vacuum of certainty, something ancient returned to science: storytelling. Physicists began to speculate in metaphors, blending observation with wonder. It was the birth of fiction at the edge of proof. The phrase first appeared in an internal NASA memo written after the October 31st meeting. One researcher described their frustration at explaining the comet's behavior without crossing the line between physics and poetry. The line proved difficult to hold. The data demanded interpretation, but every possible model contained gaps wide enough to fall through. The object had acted against thermodynamics, against the expected decay of unstable matter, and against the assumption that inert dust cannot self-regulate. Theories multiplied: resonance, plasma crystallization, magnetic memory, each solving one mystery while deepening another. Some scientists embraced the uncertainty. They argued that the boundary between hypothesis and narrative is not weakness but necessity. When phenomena reach beyond current models, language becomes the first experiment. To imagine a possible mechanism is to test the limits of known physics. The story, in that sense, becomes part of the research. 3i Atlas forced astrophysics to confront that uncomfortable truth, that exploration always begins with speculation dressed in precision. Not everyone agreed. Critics warned that turning anomalies into myth would damage credibility. They feared another Oumuamua problem: the way a few speculative papers about alien technology overshadowed years of sober research. For them, discipline meant restraint. Describe what is known, not what feels meaningful. Yet even they admitted that 3i Atlas had behaved so far outside expectation that conventional caution risked missing the larger picture. The boundary between fiction and fact grew thinner as more data appeared. The electric field signature sounded almost intentional, the synchronized pulses like a heartbeat in the electromagnetic spectrum. The comet's color shift seemed choreographed, its rotation reset timed with eerie precision. Patterns like these are irresistible to human minds. They invite story, and perhaps that is unavoidable. We are a species wired to translate chaos into narrative, to give rhythm to the unexplainable. 3i Atlas simply provided the perfect mirror for that impulse. Writers, philosophers, and filmmakers quickly joined the conversation. Essays appeared titled "The Comet That Learned to Survive and When the Sun Spoke Back." Documentaries framed the event as a parable about resilience and transformation. Within months, public fascination drifted from the physics to the symbolism. Meanwhile, in private, researchers continued their analyses, oscillating between pride and discomfort at how myth had overtaken data. In truth, the two were never far apart. The difference between a working model and a parable is one of certainty, not purpose. Both attempt to connect cause and effect. Both search for coherence in noise. In that sense, the scientific method and storytelling share DNA. Each begins with the same sentence, "What if?" By early December, the term fiction at the edge of proof began circulating in academic circles as shorthand for phenomena that hover just beyond current understanding. Not false, not confirmed, simply waiting. It became a reminder that science's strength lies not in what it knows, but in how it questions. Perhaps that is the final lesson of 3i Atlas. The comet showed that proof has texture, and its edges are porous. Beyond them lies not darkness, but imagination, a necessary light that guides inquiry forward when equations fall silent. Fiction, in this context, is not deception, but courage, the willingness to describe what might be true before we can measure it. At the edge of proof, where numbers blur into wonder, 3i Atlas still drifts, a glowing symbol of the space between certainty and belief, where every discovery begins. By mid-November, 3i Atlas had moved beyond the reach of the sun's glare. The blue glow that had once set observatories trembling was now gone, replaced by a faint white haze that faded a little more each night. Tracking telescopes followed it until the signal dropped below detection thresholds, and then, as quietly as it had arrived, the object slipped back into darkness. No explosion, no fragmentation, no final burst of energy, just a gradual dimming into nothing. Astronomers called it the return to silence. Silence in astronomy is never empty. It is measurement, signal absence, the baseline against which everything else is defined. For months, the sensors that had screamed with electromagnetic activity now showed perfect flat lines. The electric field pulses vanished, the magnetic harmonics decayed. The background hum of solar wind resumed its ordinary unbroken rhythm. It was as if the entire cosmos had taken a deep breath, exhaled, and settled back into its regular heartbeat. For the scientists who had lived with 3i Atlas day and night, the quiet felt almost physical. Research teams described it as withdrawal, the sudden emptiness that follows an intense moment of discovery. Instruments still pointed toward the last known coordinates, recording static and hoping for one more echo. None came. The data archives filled with silence, hours, then days, then weeks of nothing but cosmic background noise. The object had moved on, carrying its secrets with it. In that absence, reflection began. The excitement that had driven thousands of lines of code and endless debates slowly gave way to something more human, or mixed with melancholy. The comet had come from another star, revealed impossible behavior, and left behind mysteries deep enough to sustain decades of study. Yet the event was finite. The universe had closed the curtain with perfect timing. The silence became part of the story, the punctuation at the end of a sentence no one knew how to finish. Several research papers published afterward used that silence as data itself. One analysis measured the decay rate of residual magnetic fluctuations, treating the fading signal as the comet's final signature. Another compared the drop in ion emissions to models of plasma relaxation, finding that the energy dissipation followed the same exponential curve as cooling metals. Even in its retreat, 3i Atlas was teaching physics, the mathematics of stillness after fire. Philosophers of science found meaning in the quiet too. They wrote that the return to silence was not the end of discovery, but its necessary counterbalance. Every anomaly needs an echo of calm to be understood. Without the silence that followed, the chaos of the event would have remained only spectacle. With it came perspective, the ability to see pattern, cause, and consequence. To the general public, the disappearance felt almost mythic. News outlets called it the visitor that left without goodbye. The blue comet became a symbol of impermanence, of the beauty that exists only for those watching at the right time. Artists painted it fading into starlight. Musicians wrote pieces that began with violent crescendos and ended in single sustained tones. In its vanishing, 3i Atlas became more alive in imagination than it ever was in the telescope. By the end of the year, the last traces of its electromagnetic memory were gone. The data files were archived, sealed under mission codes, their signals compressed into digital silence. Only the numbers remain, and the questions. Did the comet change only itself? Or did it change how we see the universe? Silence has always been space's final language. It does not erase what came before, it preserves it. The absence of sound, light, or motion becomes the proof that something once existed, powerful enough to disturb equilibrium. 3i Atlas arrived as noise, magnetic, visual, electric, and departed as stillness. It left the solar system not with destruction, but with calm. The return to silence is not disappearance, it is transformation completed. The fires cooled, the rhythm faded, and what remains is understanding. Quiet, vast, and infinite.